Let's do some math for fun. Today, in this video, I am going to approximate log of 0.7 with base 0.5. And as you guys can tell, we can just basically type in this logarithmic value into the calculator and we are done. But I am going to spice things up. That is, I am going to try to use calculus to approximate this value. In fact, I am going to show you guys two calculus ways to approximate log of 0.7 with base 0.5. So the first way I'm going to use is the equation of small approximation. Recall the equation of small approximation, but for this one we are going to be involved the relationship between new and old x and y value. So I will let the original value of x equal to O of x and the new value of x equal to n sub x, and same thing, the original value of y equal to oy, and then new value of y equal to n sub y. And then what I can do here is the new value of y is equal to the old value of y plus the delta y, where delta y is equal to dy over dx times delta x, and delta x is equal to the new value of x minus the original value of x. So this is the equation of small approximation, but we are going to apply this equation to here. And in order to do that, we have to come out a function that is suitable to solve this, that is suitable to approximate this value. So in order to do that, I will let y equal to log of x with the base 0.5, and then we differentiate it, which is dy over dx. It is going to be equal to 1 over x times natural log of 0.5. So and then our new value of x is just going to be 0.7, but our closest value that we can recognize is 1, and because it's 1, which means, and the closest value that I can think of is 1. I know it's like 0.72 or 0.73, but I'm trying to not to use calculator to approximate this thing here. So I will let the original value of x equal to 1, and then because original value of x equal to 1, then the original value of y equal to log of 1 with the base 0.5, which is equal to 0. And then we can basically substitute everything, and of course the dy over dx, our value of x that we are going to plug in is x is the original value of x, and then approximately equal to. So I have everything right here, and of course when I plug in the value, then which is equal to 1 over natural log of 0.5. So we have everything right here, and then we can just basically approximate the value. So the log of 0.7 with the base 0.5 is equal to 0 because original value of y plus the delta y, where delta y is approximately equal to dy dx, where x is equal to 1, which is 1 over natural log of 0.5 times the new value of x is equal to 0.7 minus the original value of x, which is equal to 1. And then plug in everything, I will get negative 0.3 over natural log of 0.5. And then it will do simplify some more. Then this one is going to be approximately equal to, oh, I forgot this approximate sign. It is going to approximately equal to 0.3 over natural log of 2, which is approximately equal to, and then for this time we can actually do some plug in the calculator because we try to use calculus while going to so 0.3 divided by natural log of 2. So 0.3 divided by natural log of 2 is approximately equal to 0.432808512. So I will just basically write everything down. So 0.432808512. So log of 0.7 with base 0.5 is approximately equal to 0.32808512 if we try to use the equation of small approximation. And next, let's jump to the second method, or the second calculus method, to approximate log of 0.7 with base 0.5. Now let's talk about the second calculus method that are going to approximate log of 0.7 with base 0.5. And the second method is just, I think it's going to be the most effective to approximate the value because it involves repetition. And in fact, the higher the repetition, the higher the accuracy of the approximation. And that method I'm talking about is, of course, the Newton-Raphson method, or you can call Newton's method in short. And to do that, we are going to come up with an equation. And to do that, we are going to let x equal to log of 0.7 with base 0.5. Since y is the base, when we take to other side, then 0.5 with power of x is equal to 0.7. And Newton's Raphson method, what they do is they can find a root over equation, the root over equation when the equation is set to be equal to 0, and then set the left side of the expression as function, and then you can just use the formula. Because 0.5 is the base, when I take the other side, basically 0.5 power of x is equal to 0.7, which makes that 0.5 power of x minus 0.7 is equal to 0. And then we can use the Newton-Raphson method. And then what I'm going to do is, so we can finally use the Newton-Raphson method because we have make one side equal to 0, and then we set this as f of x. So I will let f of x is equal to 0.5 of x minus 0.7. And then we are going to apply the formula, which is x sub n plus 1, which is equal to x sub n minus f of f sub n over f prime of x sub n. So to do that, we are going to find the derivative of f of x. So f prime of x is basically equal to 0.5 power of x times natural log of 0.5. And then we can just basically plug in everything, f of x and f prime of x, to here, so that x sub n plus 1 is equal to x sub n minus 0.5 over x sub n minus 0.7 over 0.5 x sub n times natural log of 0.5. And as you can see that we still can simplify this, which is equal to x sub n minus, we can separate because it's a fraction and the denominator is just basically a multiple term, we can just basically break it up. So this is equal to x sub n minus 0.5 power of x over x sub n and 0.5 x sub n times natural log of 0.5 minus 0.7 over 2 over 0.5 x power of n, the power of x sub n times natural log of 0.5. And then 0.5 power of x sub n we can cancel out. So our remaining variable is going to be 1 over natural log of 0.5. So x sub n plus 1 is going to be equal to x sub n minus 1 over natural log of 0.5 minus 0.7 over natural log of 0.5 times 2 power of x sub n. And then I'm still going to simplify this. Now natural log of 0.5, which can be equal to negative times natural log of 2. So this thing is going to be equal to x sub n plus 1 over natural log of 2 plus 0.7 over natural log of 2 times 2 power of x sub n. And then we are technically done. And then the most challenging part of using Newton's Raphson method is we are trying to figure out what is the range, what is the interval of the root such that when you plug it in, the interval, the upper limit and the lower limit of the value, you will get a change of sign, and then which goes from either positive or to negative or vice versa, and then you can just basically do the rest of the job and then you get the final answer. So that is the most challenging part, because you need to randomly pick a value and then plug in until you got a change of sign, which is the positive and negative sign, and then you can just do the rest of the job such that you can find the value of x of the root. But don't worry, for this equation I can figure out what is the interval of the value of x. So here's the claim. Since I know that 0.7 is in between 0.5 and 1, which means that the log of 0.7 will be 0.5, which is the value of x, is going to be in between 0 and 1. How do I know that? Well, according to the previous video, I already showed you guys how to guess the range of a logarithmic value. So we can guess the range of this one, which is in between 0 and 1, and when we set this equation, we already know that our root the value of x, which is this one, is just going to be in between 0 and 1. And because of that, we can straight away apply this equation because we already got the interval of x. But if you're still not convinced about the interval, you can just plug in the value one by one. So when x is equal to 0, it's just basically going to be negative 0.7. When x is equal to 0, it's just going to be equal to 1 minus 0.7, which is equal to 0.3. And when x is equal to 1, it's just going to be equal to 0.5 minus 0.7, which is equal to negative 0.2. And look at what we got. We go from 0.3 to negative 0.2. There is sign change, which is changed from positive to negative. That means the log of 0.7 with base 0.5 is indeed in between 0 and 1. And because of that, we can finally use the Newton's Raphson method to find the value of x. So before we moving on, I just realized we got some mistake. So this one has to be plus, and then in that case you have plus right here, and then this should have minus because of the negative sign. So it's going to be like this. Then it's just going to be so I'm sorry, careless mistake right here. So because when I distribute, don't forget to distribute the negative sign. So negative, positive, negative, 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 positive. So I distribute, it's just going to be equal to negative times 0.5 power x sub n over natural log of 0.5 times 0.5 power of x sub n minus 0.7 over natural log of 0.5 times 0.5 power of x sub n. So the negative I forget to distribute, and I'm sorry. So we can distribute the negative sign. So negative distribute to here, we get minus. Negative distribute to here, negative become positive. So that's why we have positive. So here we should have plus, and then if we simplify, we should get minus in the end. So this is the final result of the true final result of the x sub n plus 1, which is equal to x sub n plus 1 over natural log of 2 minus 0.7 over natural log of 2 times 2 power of x sub n. So if you guys know how to do the Newton's Raphson method, we will actually pick an initial value that will satisfy the interval of the root of the equation. So in this case, I will just let x sub 0 equal to 0.5. Then x sub 1 will be equal to x sub 0 plus 1 over natural log of 2 minus 0.7 over natural log of 2 times 2 power of x sub 0, which is equal to 0.5 plus 1 over natural log of 2 minus 0.7 over natural log of 2 times 2 power of 0.5. And now if we get that, then x sub 2 is equal to, so just copy like this, x sub 1 plus 1 over natural log of 2 minus 0.7 over natural log of 2 times 2 power of x sub 1. So and then finally x3 is equal to x2, and then so basically it's just going to be repeated and repeat and repeat. And why we repeat is in order to get most accurate result of the root of the equation. So in order to make up its exact form. So in order to do that, I will just type 0.5, put it equal to sign, and then answer plus 1 over natural log. Okay, let me just redo this. So 0.5, and then answer minus, no, not minus, plus 1 over natural log of 2 minus 0.7 divided by natural log of 2 times 2 power of answer. So this should be the result, and then if I plug it in, so x sub 1, this is the x sub 1, which is approximately equal to 0.51444999815. And then if you press this equal sign again, then it will then x sub 2 will be equal to 0.514573171. And you press it again, we will equal to 0.514573172. If you press it once again, then x sub 4 is equal to 0.514573172. So because there is no decimal change right here, let's just stop here, because if we continue doing that, there's no use, because it will never show the remaining decimal digit behind the screen of the calculator. So what we can conclude is the log of x, log of 0.7 with base 0.5 is approximately equal to 0.514573172. So since we have calculator right here, let's see what if we use calculator to directly approximate log of 0.7 with base 0.5. So natural of 0.7 divided by natural log of 0.5 is basically going to be equal to exactly the same. So yeah, it's going to be exactly the same. So this is real. I type the real one, the exact form, it will basically get the same thing. So but for the equation of small approximation, it's the difference is like 0 point somewhere in like 0.8 and something like that. So for this one, the Newton's Raphson method is very effective to approximate a value. But for this one, because the one factor is the value of delta x, the delta x is like too far away, we need something that is very very close to 0.7, which is like 0.705. That's very very close. You can use that, you can use this, but it will be very very close. So for this one, for this one, the Newton's Raphson method, we have already shown that Newton's Raphson method could be the most effective method to approximate a value which is represented in the exact form. And as always, if you guys enjoy this video, leave a like and subscribe to my channel for more upcoming math videos, and I will see you guys next time.